All right, so now we'll be moving on to force. So that's where the bulk of this lecture will really be about, force and work. The kinematics was just really an introduction. Yeah, we will have examples of everything in the end, okay? And if not, I'm sure you can always find examples online. It's very easy, but we will have a couple of examples, just of general questions you may see later on, okay? And these force problems will also take into account your knowledge of kinematics. So what we just talked about will come back again for the rest of the lecture, okay? But now we want to talk about Newton's 3 laws, okay? You all probably know Newton. He pretty much, I guess, discovered gravity. Some people say it made a lot of like what we know in terms of force, equations, and acceleration, everything like that, okay? And he discovered these 3 laws, which we still haven't found an exception to them, okay? So his first law was that an object at rest will remain at rest unless acted upon by a force. An object in motion will remain in motion unless acted upon by a force. I'm sure you all know this. So if you have, say, a box, unless some kind of force acts on the box will not move. If you take the box and you throw it or you slide it, it won't stop unless something acts against it, okay? This may be a little bit counterintuitive to what you can see. So if you take like a box, obviously it'll stop eventually, and if you slide it, but that's because a force does act against it, the force of friction, okay? So you slide the box and then force of friction acts against it and the box stops. And we'll cover that much more in detail in a bit. The second law is the force applied to an object correlates to the object's acceleration. So this is the classic equation F equals ma, where F is force, m is mass, and a is acceleration, as we mentioned earlier. Right, this is the equation, this is the basic equation that we'll be using for all of our forces, essentially. And it's kind of the fundamental equation for force. And this tells you a lot. So the speed, the acceleration with which something moves, so again, speeding up or slowing down, is directly tied to its force. So if you apply a weak force on something, then it'll accelerate a little bit. If you apply a stronger force, it'll accelerate a lot more, right? And the third law is that every action has an equal but opposite reaction. When you apply a force to an object, the object also applies a force onto you, okay? Now, this is all a little bit abstract. How do we actually use this, okay? So there are many different types of forces that we'll encounter. So some of the most common and most basic are the normal force and weight. Weight is what essentially we think of as gravity, and it's what pulls you down to the ground. It's what keeps you from floating away. Weight is equal to mg, where g is the acceleration due to gravity, as we mentioned earlier. It's equal to 9.8 meters per second squared. Okay, and again, weight is a force, and it's equal to mg. If we look at this exact equation again, F equals ma, well, we have weight of force is equal to m times g, which is an acceleration. So this follows a very simple law. The normal force is the force applied onto an object by a surface that holds it. So again, every action has an equal but opposite reaction. When I apply force to the floor applies a force onto me to hold me up. Otherwise, I would sink through, right? And this is what we call the normal force. So the normal force, unlike weight, has no set formula. It is simply the force opposing other forces. So in this case, it opposes weight. So it is also equal to mg, okay? Right, and if you look at this diagram, so there's gravity or weight pulling us down with a magnitude of mg, and then you have the normal force is the ground pushing us up by an equal but opposite amount of also mg, okay? This is not, especially with the normal force, this is not always the case. It's just an opposing force that is applied from the ground onto anything that holds it, or any surface onto whatever it is holding. Okay, and I'm sure much of this is reviewed. Okay, one common thing that you will often be seen doing is breaking forces into components. So if you've learned about this in physics, forces are vectors. They have a direction, right? A scalar is something that has a magnitude. Like, for example, speed. Speed might be a good scalar because you can be moving at 10 meters per second, and that's it. Whereas velocity is a vector. You move 10 meters per second, but where? In what direction are you moving? Okay. Well, same thing with force. And somebody asked in the chat, the PowerPoint and the recording will be posted. Yeah, the PowerPoint will be posted. But yeah, forces are vectors. So this means that they have a direction. Sometimes this direction is not convenient for us to work with, right? What we can do is we can actually break this vector into components. Okay, so in order to effectively make a force diagram, which is how we solve all force problems, we must set our axes. So typically, we set our axes based on the plane of an object, right? Because of this, we must sometimes break the forces into components to make it easier. And I'll show you in the next slide how that works. So we have this object, and this is just the zoomed in version of this picture, right? It's on an inclined plane, okay? And we have two axes. So you can see this axis going this way and this one going this way. We essentially set our axes, so we could make it any way we want. We could make the axes like this and make it a perfect cross. But that's not very convenient for us to work with. The thing that's most convenient for us to work with is doing it in the plane of the object, essentially. So the object is slanted this way, so we want to make axes like this, okay? When a force is in an axis, so like you see this Fn, the normal force, is exactly in the plane of the axes, it's perfectly fine as is, nothing to worry about. But sometimes not all forces are in line with the axes. So like you see this weight is going down, but it's actually not on one of the axes. The way we fix this is we have to break weight into components. And this is where I will begin annotating, okay? So we can break this line down into two components. So we can do an arrow like this and an arrow like this. Essentially, when you add up these two dotted arrows together, you get this weight, right? But notice how these two dotted arrows are in the axes. This one is in this axis, and this one is in this axis, right? So now they're very comfortable for us to work with. Well, how do we do this? Well, how do we break something into components? Well, we have to use angles, and we have to use some trigonometry. If you notice, this is a right triangle right here. This is a right triangle. Since we know that we know this angle, we also know this angle and this angle, right? This angle is just this, and this angle is what's left, right? And again, we broke down the components over here just so it's easier to see, but we could also break the components down like this, and it's easier to see as well. Okay. And this corresponds to the sides of this right triangle, right? This is the y component, and this is the x component, okay? So if you notice that we mentioned that in order for something to be accelerating, it has to have a force applied to it. That's what F equals ma signifies. This block, pretending this block was not accelerating in this direction, right? In this direction, this axis, right? If it's not accelerating in this direction, that means it has no net force in this direction. So that means this Fn and this component cancel each other out completely and give a net force of 0 because it's not accelerating in this direction. But it may be accelerating in this direction, right, in this axis. And that's likely what the case is because we have this component, this vector component, going along that axis in the left, towards the left, but we don't have anything canceling out going to the right. So likely this object, this thing on a ramp, is accelerating this way. How do we find out what the value of the components is? Well, we use simple trigonometry. We know what the value of the hypotenuse is, this long side, because it's weight and it's usually given to us. mg is given to us. And we know what the angle is, because that's also usually given to us, or maybe it might be the unknown that you're trying to solve for, either way. And we know that, and we know this angle, and we know that sine of this angle is equal to opposite over hypotenuse. This is the hypotenuse. This is the opposite we're looking for, so we'll call this x because it's a variable, so we'll just call it x, and it's equal to sine alpha or theta or whatever this angle is, right? And this is how you do it. And if we want to solve x, it's just mg sine alpha is equal to this x component. If we have this component, we'll call it y. That opposes the normal force. Well, it's just mg cosine alpha. Okay. Does that make sense? Does anybody have any questions? Please put in the chat or raise your hand or speak up if you have any questions. Okay, so if no questions, we'll continue, and you can always come back and ask more questions in the chat if you'd like to. Okay, so we talked about two forces, the normal force, Fn, and the weight, Fw. What are the other different types of forces? Well, the next most common is the force of friction. The force of friction has the formula F equals mu times normal force. So friction always opposes movement and prevents sliding. Like I mentioned earlier, if you take a box and you just slide it on the floor, eventually it'll come to a stop. Normally this would violate Newton's first law, but it doesn't because there's a force of friction that acts against the box. It's the floor acting against the box, and it's going in the opposite direction to prevent it from sliding further. Okay. So there's two types of friction. There's kinetic friction and there's static friction. Kinetic friction is the friction when you're moving an object that is already moving. Static friction is the friction when moving an object that's at rest. And one way you can remember this is that static friction is always greater than kinetic friction. It's always more difficult to move something that's at rest than it is to move something that's already moving. Why is that? That's because the static friction is much higher than the kinetic friction. So the force that's opposing you when you're trying to move something is higher when when the object you're moving isn't already moving. Okay. And if we want to go back to our picture, if you were to draw how the force friction would look, the force of friction always prevents sliding, right? Well, we already decided that overall this box is moving this way, right? Because gravity, it's moving this way. Well, if it's moving this way on a surface, the force of friction will be opposing that, and the force of friction will be this way, like that. And it depends if the force of friction is exactly equal to this force that we already determined, then the object will not move at all. They'll perfectly cancel out, and the object will have no acceleration. I shouldn't say not moving, it should have no acceleration, right? It could be moving at a constant speed. If the force of friction is greater, which will never happen because friction can't be greater than something like that. So it'll actually won't go this way. But if the friction is less than gravity, then it'll just keep going this way and keep accelerating that way, I should say. Okay.
Quick question, Mark. In the previous example, did you use how did you determine that the angle was alpha? Between the W and the arrow, the blue arrow. Were you using
so that's something you just have to kind of know. It involves trigonometry. I believe it's called, I don't remember what the principle was called. It was
similar. I think it's similar angles.
Yes. So, but just something you have to remember, like when it's like this, and if you're drawn like this, when you do enough of these problems, you'll kind of like memorize it, and you don't have to do it like that. I'm echoing Kajia, thank you. And just this one is alpha, and then you know that this one is just opposite of alpha because it's a right angle, right? That is just something you pick up when you're doing enough of these problems, right?
Fair enough. Thank you.
Yeah, if you go more into like geometry and trigonometry, then you'll probably like remember exactly what the principle was called. But the MCAT really, it's not testing on trigonometry, so
yeah, I think it's like similar angles or something like that. Yeah, it sounds familiar.
Yeah. Okay. So that's
Mark, I have another question following that.
Yeah, please.
So we're finding the value for X. So what exactly we're finding the magnitude of? I was just trying to figure out what you were solving for. Because was that angle given?
Right.
That theta,
right.
like we're assuming theta is, or alpha is something.
Right. Yeah. So because it depends on the question, but the general formula is that's an alpha. Just pretend that's an alpha. Sine alpha equals x over mg. Right. This is what I drew before. X is this component. Right. So what they may give you is they may give you alpha, they may give you mg, they may give you different things. They may ask you to find x, they may ask you to find alpha. I don't know what the question is going to ask you, but this is the general formula, and you just have to fill in what you already know. Sorry. So they may give you alpha, and you know that this is alpha, right? If this angle is alpha.
Yeah, I got that part. But what is x?
X is this component of, you see how this vector is not in line with the axes. This is the axes that we set. It's not on the axes, so we can't actually use it. But we can break it down into two components that are each on a different axis. So I'm going to draw it over here. If you have an arrow like this, you can break it down into a downward arrow and a rightward arrow. And when you combine these two dotted arrows, the product or the result will be this one arrow, right? So we can do the opposite. We can break down one arrow into two arrows. So we broke down this one blue arrow, the weight, into this arrow going down and this arrow going left, right? Because these two arrows, you see how this arrow is on this axis and this arrow would be on this axis. So they're actually on the axis, and we can use the two arrows, but we can't use the one arrow. So we want to break it down into two arrows. In order to find what this one arrow is, if you want to look at this graph as like a right triangle, look, this is a right triangle. This side of the right triangle, this one right here that I'm keep highlighting, that's what this rightward arrow is actually equivalent to, right? And we know laws of right triangles from trigonometry. So therefore, if we find out what the value of this arrow, of this side of this triangle is, we know what the magnitude of this arrow is, this force vector. Does that make sense?
Yes, thank you.
No problem. Any other questions? Okay. Let me clear the annotation, sorry. Okay, so let's move on to other forces that we could possibly have. So we just talked about friction. Well, the other forces are tension and spring force. So tension is a force that is always present when there is a string or a rope involved. Spring force is a force that is always present, as the name suggests, when there's a spring involved, right? So if we pretend, so before we had friction opposing gravity in this thing, where friction was pushing it to the right. So if the overall movement of this block is this way, now pretend the slope is ice. It has like very low friction. Friction can't oppose this. But now you have, say, a string. So pretend this line is like a string hooked onto here, right? We can use a string to oppose this movement downwards. So in strings, the force caused by strings is called tension. And tension also opposes movement. So if you want to think about it this way, if the string is tethered to a wall or to somebody holding it essentially, and the block is going this way, the string will actually end up pulling the block back up because it doesn't want to move, like from its tether point. So it actually ends up pushing pulling the block up in this direction. So tension would be going in this direction in this case. It would oppose this movement, right? And it's just tension is just the force caused by this string. Okay, and we'll get more into that in a bit. The other option is if you had a string. So again, a spring, I should say. So and springs, there could be a spring here. So this is a spring. And gravity is pushing it towards a spring. So you guys know how springs work. They stay in one position in the rest form, and then they would like to stay in that rest form. If you compress a string, it'll bounce back to its original position. Same thing here. You apply a force down to compress the string or the spring. The spring will apply a force to oppose it to make it go back to its original, to make the spring go back to its original position. In this case, if the spring is this way, it'll be applying a force this way in order to go back to its original position to stop itself from being compressed. This would be the spring force. If, on the other hand, you were to do something very similar to the string, where you would tether a spring on this side, well, the spring would be elongated, and it doesn't want to be elongated. It wants to go back to its original position. And that, so what it would do is it would try and snap back, and it would apply force in this direction to kind of go back to its original position, right? The key with springs is they always want to go back to their original position, and they always apply a force towards their initial position. Whether if it's compressing, it goes outward. If it's elongating, it's going inward. And I actually have a string right here, a spring. So if I try and, this is its initial position right here. If I try and elongate it, it gets harder and harder because the spring is applying a force in this direction to counter my elongation, and then it just springs back, right? Does that make sense?
Yes, quick question, Mark. You could go back to that diagram you just had.
Yeah, sorry, and we did put in the chat Hooke's law. It's right here. Yeah, I was gonna get to it in a second, but yeah, Hooke's law is F equals kx. But yeah, go ahead. Sorry, I cut you off.
Yeah, my question is, Opal, real quick, can you mute one of your computers or one of your tablets?
I did. I muted the computer.
Like also turn like the volume completely
Oh,
off
the
of
volume
one.
down. Okay, that makes sense. Okay, so Mark, you did say third law says force up equals force down, like the normal force is going to negate the weight. So why do you have that arrow going off, the blue arrow going off to the side? Shouldn't it be going straight down?
No, okay. So what I said was weight, no matter what you do, no matter what position you're in, no matter what, gravity always points directly down. No matter what, it always points directly down because that's just how gravity works. It always goes straight down. The normal force doesn't always go straight up. The normal force always goes up from the surface. So if the surface is slanted like this, the normal force would go up from the surface and it would actually go right here, right? So the normal force doesn't oppose gravity. It comes from a surface and it always pushes off the surface, okay? Since gravity is always pointing down, but it's not on the axes, we have to break it down into components. Yeah, as Janelle mentioned in the chat, normal force is always perpendicular to the surface, whereas gravity is always pointing directly downwards. But downwards is not always the direction we set our axes. So in this case, we set our axes along like this, not along gravity.
Thank you. Makes sense.
Okay. Any other questions or should I move on? Okay. All right. So I was talking about tension and spring force. So like I mentioned, tension is somewhat similar to the normal force. It also doesn't really have a specific formula. There are formulas that you can find online, but usually tension, especially how they give it to you on the MCAT, is more a force that you have to figure out based on like opposing factors, right? So they may give you something hanging on a string, and you know that the object is not accelerating, so you know the net force is 0. If you know the net force is 0 and you know the force of gravity, you'll be able to find out what the tension is, right? Because it opposes gravity and acceleration is 0, right? Otherwise, it could be given to you in the problem. Spring force does have a formula, and it's the same formula that was put in the chat earlier, Hooke's law, where the force of spring is equal to kx. K is the spring constant. There's not a set value for the spring constant. It depends from spring to spring. Each spring has its own spring constant, and they'll give that to you. Or they may ask you to find that. X is the distance of the spring currently from its natural position. Like I mentioned, if you have this spring, this is its natural position. Right now, it's expanded. So whatever its distance is right now, subtracted from the distance it is right here, the difference in distances is what X would be. So the more you expand, like I mentioned, the more you expand a string, the harder and harder it gets to pull, because the force is getting bigger and bigger of the spring force getting bigger and bigger, right? And any questions on this before we move on to our first clicker question? Or our first poll question? Yes, tension. So tension is always a force on a string or a rope, right? Or any kind of like pulley, right? So how you figure out the formula? So usually there's not really a formula for tension. It's more you have to kind of see it, and I'll give you a question I think later on where we talk about where we ask you to find tension, right? So yeah, for example, if they give you a very, very simple situation where they have a string with like a box hanging on a string, right? You know that the force of gravity on the box is always going down, directly down, and the tension is going directly up. They're in direct opposition. If you are told that the box is not accelerating up or down, you know what the net force is 0. If you know what the force of gravity is, you know that the force of tension is exactly the same as gravity, just in the opposite direction. Because of that, you can then just equate tension to mg, and you can find out what the tension is, similar to how we did the normal force, actually. right? K constant it's the spring constant, and it depends on each spring. So if you want to, sorry, if you want to think about it like kind of like the elasticity or whatever of the spring itself, but they'll always give you what K is. It's just what the specific constant for the specific spring they're giving you is. So I don't know what the K constant of this spring is, but whatever it is, it's just what it is for this spring, and a different spring would have a different K constant. Yeah, okay. And they may ask you to find what the spring constant is for a spring if they give you the force of the spring and the distance, the x. So it's very simple. Yeah, it'd just be, yeah, it's essentially the stiffness or elasticity. All right, so I'm gonna start this poll. If you guys wanna give it a try.